Good morning. Thank you all for coming to this district cooling seminar. It's an honor for me to be here with you, members of the Estonian Association of Thermal Engineers. My name is Maria Jangsten, and I'm a PhD student at Chalmers University in Gothenburg, Sweden. And I collaborate with the utility company Göteborg Energi. Their logo is there. And today I will talk to you about district cooling in Gothenburg, and also the research that I do on the district cooling temperatures in collaboration with the Gothenburg Energy. So just to give you an overview of this next hour, so you know what's to come. First, I will go through, let's see, is this the pointer? Yeah. This first part will be about the district cooling system in Gothenburg, a little bit about the development of the whole network, and then a little bit of production, and so on. And then when I go over here to talk about the temperatures in the system, that will connect with the research project that I'm conducting. And I've been doing this for the past 2 years, so I'll go through a lot of results. And they have to do with the low delta T in the system, and also a little bit on the potential of using higher temperatures than the traditional temperatures. And then I'm trying to summarize the experiences from Gothenburg. Okay, so we'll get started. This is a map of Gothenburg, and this is how it all started out, this cooling system, back in 1995. So they started with building all these blue dots that you see across the map, which are individual little cooling islands, serving one or a few buildings in each of these areas. So we started all the way over in the east with the hospital, and then one out in the west in the port, and in between, so this is the downtown area of Gothenburg here, and so they were spread out throughout the city. Until 2002, they constructed all these cooling islands, and then the total installed capacity was 24 megawatts. And then if you zoom in a little bit on the central area of Gothenburg and a little bit to the south, and I just wanted to provide you with a reference map of Tallinn, so you know approximately the distances and the area we're talking about. So this should be the same scale for these two maps. So we continue with this little bit zoomed in map of Gothenburg. That's where the district cooling system took place and the development of the network. So from 2002, they focused on these cooling islands, and they also built one on the north side of the river in Gothenburg, in Lindholmen. And they started building pipes from the cooling islands out to more buildings. So this is 2002, and then more pipes were added on to the system. And in 2007 to 2008, we got a big production facility here in this area. They added 22 megawatts here. And then they continued expanding the system and added some more production here in Rosenlund in this area, which is close by the river, and continued expanding, adding more pipe. And then in 2013, they decided that we need to focus on densifying the pipes we have, or the customers that are located to the network that was had been built so far. And then they added more pipes until today, where the system looks something like this. So we have still 3 blue dots, which are still the cooling islands that were originally built. These cooling islands are a total of 17 megawatts. But the main district cooling system is this network now. This is a connection in a tunnel up to the hospital here, and then it's all of the downtown area and down to the south. This is the famous amusement park, and a little bit south of that. And the network on the north side of the river, Lindholmen, that's still a separate network. So technically today, it's one large system in Gothenburg, and then it's a small system on the north side of the river. But the Gothenburg Energy likes to refer to it as one district cooling system, although so far it's still 2. And the total installed capacity between these 2 networks is now 72 megawatts. But if we look into the future, the plan in the next 10 to 15 years is to build a pipe underneath the river and connect the two district cooling systems so they become one eventually. And this is actually ongoing work already, so they have started to drill that pipe underneath the river. And then the plan is also to add more capacity, and up here there's supposed to be a tank, cold water tank, or thermal energy storage, and some more major pipelines will be built in different parts of the city, and more production will be added also in each sort of corner of the network to provide for the increased cooling demand. And so when this has been done, the total installed capacity will be around 163 megawatts. And so it's more than a double of the current installed capacity that we're looking at. And that's because Gothenburg is actually growing quite a lot. There's a lot of densification in central areas, a lot of potential development going on in this area, also along the whole river up to here. So there's plans of adding on into the city development in different stages. So with that, the cooling demand is what's growing in the city. Meanwhile, the heating demand is more or less going to be constant during this time period. And the delivered energy, if we start in 1995, when they started building the cooling islands, up until today, has grown from nothing up to around 100 gigawatt hours. That's approximately what they produce per year now. And so this is the projected, the green bars here are added on the projected cooling demand because of the expansion of the city and the increased demand for cooling. So it's going to be more than 200 gigawatts by 2035. So if we look at, well, this is a nice simplified overview of the district cooling system. And now I want to go into a little bit more about the production of the system, so this part of it. And Gothenburg has a lot of waste heat. That's why the district heating system in Gothenburg was developed in the 1960s. And that's because there is waste incineration plants, and also there's two big refineries in Gothenburg with a lot of waste heat. So this waste heat is very good to use for cooling in the summer when there's a low heat demand. And also there's a river in Gothenburg, and that river is used for free cooling when the temperature of the river allows. So yeah, the waste heat is good for absorption chillers, and the river is good for free cooling. And then of course we also have electric chillers for backup and peak production. This is the cooling demand of Gothenburg, and I wanted to show two different years, because these 2 years were very different in how nice the summer was. So 2017 was a very cold summer, and 2018 was a really warm summer with heat records and amount of hours with temperatures over 25 degrees. They were far more than ever seen. So the cooling demand in 2018 was up to 50 megawatt hours as most. And these peaks were a lot more than they were in 2017. So with this, it shows that the outdoor temperature and the conditions during the summer, they very much decide on what the cooling demand is going to be. And especially the peak hours in the summer, which is the tricky part for the production facility to meet. And back to the absorption chillers, so the waste heat is what you can see here in the green and also the blue. This is throughout the whole year. And the heat demand is this black curve here. So in the summer, there's a lot of waste heat, the green area here, that would have to be cooled otherwise away to the birds by cooling towers and so on. So that's why it's very good to use the absorption chillers to take care of this excess waste heat. And it's around, the waste heat is close to 300 megawatts during the summer. So this is what the production mix looks like in Gothenburg district cooling system throughout the year. And as you can see here, during the cold months in the winter and also in the beginning of winter in December, the river is used to produce the cooling. And the total share of free cooling is around 22%. in the whole system, depending on the temperatures of the river. And then the absorption chillers, they are the main supplier of cooling in the district cooling system in Gothenburg. Their share is about 47%, and they're started up when the heat demand has dropped, and it varies a little bit, but usually it's more around May when the heat demand is low enough, then the heat is available at zero cost for the absorption chillers. And then for peak production, and also here in the fall, when the heat is mainly used in the district heating system, then the electric compressors chillers are run to produce the cooling. But the absorption chillers, the main supplier of district cooling. And just to give you a sense of how well the system performs throughout the year, the COP for the large system in Gothenburg is actually up to around 20 in the winter when the free cooling is used. And then it drops down to around 7 in the spring and summer, and then it does a little bit of a dip here when there's a lot of compressors in the beginning of fall. But in the winter, the COP gets really high, and this includes also the distribution pumps. So not only the chillers in the system, but everything combined. And I also want to show you how much district heating that's needed to produce the cold water. So the red line here, this is how much district heating that is used per month in order to produce this amount of cooling, and also how much electricity that's needed, so we get a sense of the scale of the energy needed here. So for example, in July, around a little bit more than 16 gigawatt hours of district heating is needed to produce almost 12 gigawatt hours of district cooling, with 1.5 gigawatt hours of electricity for the month of July. And a little bit more on the absorption chillers. There is one issue, although we have a lot of waste heat from the industries, the refineries, the district heating network, it's around 90 degrees of available heat to the absorption chillers. But the absorption chillers, they return 80-degree water to the district heating network. So the cooling of the water in the absorption chiller is not very high. It's only a delta T of 10 degrees. And this creates some problems with the district heating system. The return temperature is way too high for the district heating system. And it also leads to a very high flow rate through these absorption chillers because of this low delta T. And this was something that Gothenburg Energy did not think of when they ordered these Broad and York machines when the system was under development. So today on the wish list is at least a 20 delta T in the generator of the absorption chillers. So they're looking into ways of either replacing the current heat exchanger in the generator, or maybe they have to actually replace them, because right now they cannot invest in more absorption chillers in Gothenburg district cooling system, because it's maxed out the amount of district heating water that can be used in them because of this low delta T that the chillers have. So if we move over to free cooling, then the temperature of the river, it varies like this throughout the whole year, and also between different years. So each line here represents a different year. And this is they take out and clean the temperature sensors, so it doesn't go up. Unfortunately, it doesn't jump up to 20 degrees in spring. But it's good for the district cooling system, because when the temperature of the river is 5 degrees or less, the river is used for 100% free cooling. So no chillers are needed. And with these 5 degrees, there are heat exchangers in the production facility with a 1 degree temperature approach. So with 5 degree river water, we can get 6 degrees in the district cooling system. And also, when the return temperature of the district cooling water in the network, when that is lower than the river temperature, so it should, let's say it's 15, I will come back to this, but when the return temperature of this cooling system is lower than the river water, it can pre-cool, the river pre-cools the returning chill water before it enters the chillers. And that is what's called the combi operation. So then the amount of free cooling that can be used, either 100% or in the combi operation, that's dependent on what the return temperature of the district cooling system is. And so this you can remember to later on in the presentation. And here you can also see the intake of the free cooling. It's out in the river. This pipe is 2.5 meters below the surface. This is when they're putting it in. And the pipe dimension is 1.5 meters. And it goes into the production facility where the chillers absorption and the biggest production facility that we have. Okay, now it's time for you to actually take out your smartphones. And it's like a check for me to see that I made sense. Yeah. Oh, okay, yeah. So if you haven't done this before or you're not familiar with it, you go to this website, menti.com, and then this is the code that you enter in the little field, and there should be a question.
Can I also talk in Estonian?
Yeah, yes, please do.
Maria, palun, tahate kaasata ka küsitluse juurde, et tegelikult ma pakun välja, et kõigil on mobiiltelefon kaasas. Et tegelikult te peate tegema ühe asja, minge palun menti.com aadressile ja toksige sisse see number ja siis tekib paar küsimust, et Maria jaoks on väga põnev nagu saada teada, mida teie arvate sellest kaugjahusest, võib-olla saada teie mõned nagu teadmised kätte. Ma pakun välja, et kokku siin 100, et siis ootame ära, et olekski kuskil 100 vastajat. Okay, so Maria, how much time will give?
Not a whole lot.
Okay.
Did you get a question?
Yes.
Yeah? That you were able to fill in
Only one.
Yes, yeah. Okay. Okay.
One question?
It's only one question.
Okay.
And I will actually try to see if I can bring up the results.
Okay.
Oh. Okay, good. This is good.
And I suppose, Maria, that will also can get a name who answered not correctly.
No, it's anonymous. Don't worry. It's and I want to point out that these are not wrong. This would be wrong answers, but it's right now it's absorption chillers that are the mainly throughout the whole year. Good. Then we can move on in the presentation. And then we move on to the distribution system. And the distribution system has been designed for a supply temperature of 6 degrees and a return temperature of 16, so that gives a delta T of 10 degrees. And the pipes used in the distribution system are PE 100 polyethylene pipes, and they have a very long asset life, possibly more than 100 years. Compared to steel, they're completely rust and corrosion free, and they're also quite easy to install compared to steel pipes, because you can use this handy little squeeze tool and easily cut them where needed. In Gothenburg, we only insulate the supply pipe, because when the pipes are located quite close to the surface, and in the city where you have a lot of concrete and asphalt, it gets quite warm on the surface, which actually heats up the supply water. So the supply pipes are insulated, but the return pipes are not insulated, and they're also not insulated, neither supply or return, when we have to do directional drilling, which means that you have to push the pipes through the ground, such as now when we're connecting the two networks, and they're using directional drilling underneath the river to go through ground. So no insulation on those pipes. And I just wanted to show you some pictures on how it looked like when they were installing the pipes in parts of the city. You have these two guys here for reference of size, and compared to district heating, the sizes, pipes, valves, everything for district cooling is around 4 to 5 times larger than district heating because of the small delta T that the system has between supply and return. So larger pipes, more expensive. That was that about the distribution. Now I'll move over to the customer connections and mainly what happens here in the substation. And in all the customer substations or in the building connections, there are heat exchangers. And it's around 124 customers in both systems, roughly 104 in the larger and around 20 in the smaller. And it's only commercial buildings that have district cooling in Gothenburg, no residential. And right now, I don't think there are any plans either to connect residential. And these buildings, they use the cooling for mainly comfort cooling, but there's also some process cooling and servers. And some customers use it for refrigeration and mainly to cool the condenser side of different refrigeration machines. And here you can see a schematic of the substation. Here's the heat exchanger, and this is the district cooling or the distribution side, which I call the primary side. And here, the equipment that is installed, this is needed in order to send out the invoice to the customers. So the district cooling provider measures the temperatures, supply and return, and also the flow and calculates the energy in the energy meter. And they own this equipment, the district cooling provider. However, all the customers in Gothenburg district cooling system, they own the heat exchanger and they own the control valve. And compared to the district heating side, the utility provider owns all the substation and all the equipment there. But it's the other way around in the district cooling system. The pressure difference across the control valve is between 100 and 600 kilopascal. So it's quite a large range they have to control over. And it is the building system, the building management system, that controls how much this control valve should open and close depending on what the cooling demand is in the building. And the building management system, they always measure the supply temperature, and in most cases they also measure what the return temperature is, and then also more in their systems depending on how sophisticated the control and what they have decided that they need for the buildings. And just a little bit back to the temperatures. So this is what the district cooling system has been designed for, as I mentioned before, 6 degrees supply. They want 16 degrees back. And based on these temperatures, there are recommended design guidelines for all district cooling systems in Sweden that suggest that the buildings should have 8 degrees supply temperature, and they should return 18 degrees. So you allow for a 2-degree temperature approach across the heat exchanger between both supply and return streams. However, these temperatures, they are the same throughout the whole year. There's no variation depending on the outdoor conditions or the cooling demand of the building. So the utility, Gothenburg Energy, they supply 6 degrees throughout the whole year, more or less. They go down a bit lower in the winter if the river is colder. And they want 16 degrees back all year round. And with that, they also expect building owners to use 8 and 18 all year round. However, there is some ranges allowed, but these are the bottom baseline temperatures, so to say. But here you see what the temperatures actually are in the district cooling system. And this is data from 2017. And this is their supply temperature, which is not really exactly 6 degrees, but it varies, and they're allowed to go up to 7. Sometimes it goes a little bit higher, depending on how their production goes. But here you have 16. And this is the actual return temperature. So it's around 10 degrees in the winter, goes up to maybe 13 degrees on a good summer day. These are the temperatures for the large system, so it's not including the smaller system on the north side of the river. But this is the reason why Gothenburg has the low delta T syndrome. The design temperature is essentially never reached in the system. And this leads to more water flow rate having to be pumped in the system. They have to turn on more chillers in order to supply the cooling demand. And it's basically just more expensive and a waste of energy. But it's good because I have something to do. So this brings us over to my research project. And in a pre-study done to my research project, it was identified that the temperatures can be increased, just what I showed you. They're not what they should be. They're not reaching the design temperatures on the return side. So with this, reduced operation costs can be achieved. And also the share of free cooling can be increased. So now you already know that the river is used for free cooling around 22% today. But with the combi operation, the river can be used more if the return temperature wasn't around 12 degrees on average throughout the year. If it was actually 16, the river can be used a lot more for free cooling as a total share of the year. So the purpose of my research project is to investigate the low delta T syndrome, what can be done to increase the temperatures, and then also explore the potential to be using even higher temperatures than the 6 degrees supply in the 16 degrees return, because then the share of free cooling can go up even higher, as you will soon see. And this is approach from the customer side. So the utility company has quite little knowledge of what's going on the other side of the heat exchanger. So that's where my research project is approaching this issue from their point of view, by increasing the knowledge of the connected customers. And this has been the method so far. I have collected data from essentially the substation, this you already saw, from what the district cooling provider the data they measure on the primary side of the heat exchanger. And I collected data from 37 buildings, it turned out to be in the end. 29 are in the large system and 8 are in the smaller system on the north side of the river. And on the primary side here, what data that's available are the temperatures, but also the flow and the cooling power. But I also went into the building owners' building management systems and collected the data that was available on this side, which was a lot of information about the systems and mainly the temperatures that they log there, and also how much they open this control valve. But yeah, primarily temperatures. I did this during the summer 2018, which was the really warm summer. So that was good from the sense of collecting peak cooling data. And I also complemented this data collection with some flow measurements on this side of the heat exchanger in the buildings, because they measure the flow here, but not on this side. So that turned out to be a little bit of a missing link in order to understand what happens fully. And then, yeah, I analyzed the data and also had some workshops with the customers to reconnect with them and discuss what it looks like and why and what we can improve. So this is what I'm going to show you the results from now. But first, let's have another little Menti question so you don't fall asleep out there. This is a trick question, I should add.
This question is a little bit more complicated, yes?
Yes and no.
Siis küsimus jah, kus asub Göteborgis kaugjahutuse sissevool, kus nad õntuvad kaugjahutust? Kumba tõle kaudu?
And that's about everyone. Did anyone answer all three?
All three. Can be.
Yeah. It's actually basically the same picture, but from different. So this is the intake, and it's here also, and it's zoomed in here.
No wrong answer.
So no wrong answer, no. Everyone was right. All right. So we start the results with what happens in the connected buildings systems. And it turned out that all the buildings that I investigated, they are unique in their own way. It depends a little bit on how big they are and what the cooling demand are, but also what the property manager, what they invest in terms of control systems, and how much they work with the systems. But there was no building that really looked like the other. And compared to district heating, it's easier to just classify, let's say, multifamily buildings into one category. But here, in terms of what the systems they have in the buildings. But here, it was a very wide variety. But nevertheless, it was possible to see that most buildings have some sort of ventilation system that have cooling coils supplied by district cooling. And then they also have a water-based system, either fan coil units or chilled beams, or a combination of all three. But the most common was to have some sort of cooling coil inside air handling units with either one of fan coil units or chilled beams. And the temperatures in these systems is what you can see here. The supply temperature and the return temperature, and also the range for the buildings together when the outdoor temperature is more than 23. So in the summer, quite nice summer conditions, I'd say. For the cooling coils, you can use both very low temperatures, like 7 degrees, up to quite high temperatures of 18. And with that, the return temperature is also quite a large range. But what's important here is that they don't all use 7, a lot higher temperatures than that were seen. And when it comes to the fan coil units, there weren't as many, so this is a lot fewer systems that these temperatures are collected from. But they use either low temperatures, both supply, return, 8 and 10, or they use higher, such as 14, 18, supply, return. And for the chilled beam systems, these are dew point regulated, so there's no condensation system from the chilled beams, so they have to supply higher temperatures, so it doesn't start to rain inside. And they were around 14 to 16 as the lowest, but they could go up to a lot higher depending on what the dew point temperature of the air is. And all these temperatures together for all the 37 buildings, this is what the aggregated supply is just on the secondary side of the heat exchanger, and also the return temperature. And then we can compare these temperatures to the design recommendations I mentioned before, and also what the district cooling temperatures is on this side of the heat exchanger. And then we can see that what the actual temperatures are deviate quite a lot from the design temperatures. And the main, what sticks out the most is that not everyone uses 8 degrees. Well, some uses actually lower, which is quite okay. But some actually use a lot higher temperatures in the summer. And the return temperature always, of course, is an issue, which I will come back to, or which I will show here actually. Here you have a compilation of 12 buildings that have both supply and return temperatures available. And what you have here on the x-axis is the outdoor temperature. And what's interesting here is that not all buildings have set the supply temperature to 8 degrees, regardless of outdoor, but a lot of the buildings actually have this curve. So the outdoor temperature compensates the supply temperatures, just like on the heating side. So the temperature is high when it's colder outside, and it drops lower when it gets warmer. So they don't use 8 degrees all the time, regardless of the outdoor temperature. But when it comes to the return temperature side, there is everything, basically. And you have 18 up here. So there is both lower temperatures, higher temperatures. And that's, of course, this is a problem, that there's such a wide range here. And of course, it's positive for these buildings that have a higher return temperatures than the requirements. So this is, I should have mentioned this before, but this is on the building side of the heat exchanger, what you see here. If we move on to both sides of the heat exchanger, so building plus district cooling side, this is quite interesting because if the utility provider only has data from here, and with this being the supply temperature, we still have outdoor temperature on this axis here. This is the supply temperature, around 6-7 degrees, but here is the return temperature for this substation. If you didn't have this side information available, you would think that, okay, well, it looks good, and then when the temperature gets warmer, the return temperature drops. Probably because this customer doesn't have a good return temperature on the building, in the building. But when we have temperature from the building, we know that that's not the case. This customer has a really good return temperature on this side of the heat exchanger. So there has to be something else causing the temperature to drop like this. So this is when we decided to measure the flow on on both sides. So this is available. This side we measured last summer. And the fact is that the heat exchanger, or most heat exchangers, are designed to have the same flow on both sides here. But what we saw in this substation is that the primary flow, which are these orange peaks, go up to here, compared to what the secondary flow is, this blue line. It's not negative flow here, it's just the flow the measurement equipment couldn't detect the low flow. But anyways, it's a large unbalance between the two sides of the heat exchanger. And this is what caused the return temperature to drop here. These low temperatures here are connected to the higher flow on the primary side, which was caused by the supply temperature being too close to one another. So the building owner set the supply temperature, let's say, at 7 degrees. And then the district cooling temperature was maybe 6.5, maybe up to 7 sometimes, which caused the control valve to open, fully open, and the flow through the heat exchanger on the primary side. So here, this flow here gets way higher than what it is on this side. So, and then consequently causing the return temperature to drop. And then I want to also show you what it can look like when you compare the performance of different buildings on the primary side only. So here is the temperature data, which is the delta T, which is these red crosses. And then the cooling power are these blue circles. And then it's normalized, so divided by the maximum. And you have the flow here, delta T here, and cooling power here. And this is a quick way of getting a feeling for how well does this substation perform, but also to find out what the trends are for delta T, the temperature difference, which is connected to if the flow on the building is variable or constant, but it's connected to more things as well. However, in this building, you can see that the delta T is 10 degrees, which is illustrated by this line, when the flow is low. And then it just slowly drops for an increased flow rate. And that was one trend observed, which was the most common. And that says that, okay, the flow on the building side is variable, so then this is the behavior of delta T. So to say, it's going to drop when the flow increases, and it will be high when the flow is low. Another trend that was observed was that the delta T instead increased for increased flow. And that in this building should have constant flow on the building side. However, here is 10 degrees. So this building is actually not performing quite well because it's not even close to 10 degrees at any time or any flow condition. However, what's important is what the production plant is struggling with is when everyone has the highest cooling demand. And that is, of course, when the flow is the higher. And what was observed for almost all the building is this so-called saturation zone, which I have illustrated by these boxes. And what that means is that for the highest cooling power, you can see these blue dots when they hit the number 1 up here on both axes. Whatever flow rate more than this point, that's just a waste of flow, because you get the maximum cooling power for a flow that is around 70% of the used maximum in this substation. And the same for this one. Here is maximum cooling power for a flow around 40% of the used maximum. So everything else besides this, that just causes delta T to drop, and you don't get more cooling power for a higher flow. So it was actually observed that 72% of the buildings, they can use 80% or less of their maximum flow rate, and their maximum meaning that the flow rate that has been measured during the cooling season of 2018. So most buildings actually use too high of a flow rate, and that is connected to what I talked about before, how much the control valve opens depending on the settings of the supply temperature set point in the buildings. But what this means is that it could be good to actually have some sort of flow restriction here on the primary side, depending on what the building actually needs. So for this one, maybe it's good to limit the flow not to get higher than 70%. Because here the primary side just has to pump more water, and you don't actually get more cooling power out of it. And now a little bit on how much free cooling that can be used in connection to the temperatures. So this one you recognize from before. This is the supply and return temperatures from 2017, and also the river temperature for that year. And with these temperatures, the free cooling share for the production of 2017 was actually 28%, corresponding to these green areas. So that's free cooling in either free cooling 100% or in the combi operation. And the rest in the gray, this is produced with cooling machines. Now, if the low delta T was to be resolved and 16 degrees were actually achieved on the return side, then the share of free cooling would jump up to 34% of the total production over the year, which is a 6% increase. So this is if the low delta T syndrome was resolved. But we know already from the results that the buildings, they use temperatures in this range in the summer, but it leads to return and supply temperatures. Well, the supply is always around 6, but the return temperature varies. This is throughout the whole year between 10 to 14 based on the previous graph. But I also want to mention that the so-called high temperature cooling systems, which use higher temperatures, hence their name, these are becoming more common in buildings, in office buildings, because you can use higher temperatures such as 17 for the ventilation, depending of course on what the dehumidification requirements are for certain buildings, but this has actually been installed in an office building in Stockholm. And they use 20 degrees for their chill beams, and these together return around 23. So that opens up for possibilities on the district cooling side. If many buildings were to actually employ these high temperature cooling systems to supply something that is higher, around 12 to 14, and be able to get a higher return temperature, let's say 20 to 22. So with these temperatures, if we select 12 supply and 20 return for the district cooling system, for Gothenburg that would mean that the share of free cooling would be almost 55% of the whole year, more than half the cooling production of the whole year. A 26% increase. So with that, I'm going to try and summarize everything. And based on the increased knowledge of the customer connections and their buildings, we now know that there are some opportunities, such as buildings that already use higher temperatures than 8 degrees. And also the fact that they don't use the same temperature throughout the whole year. So when the temperature outside is lower, the outdoor temperature compensate the supply temperature, and it's higher. So that's what this means here. The supply temperatures are outdoor temperature compensated in many buildings. However, there are also some issues that we have seen in the connected buildings, and it's mainly linked to the fact that everyone does it their own way, basically. There's a lot of different building management systems and the way they are controlled. Some are much more sophisticated than the others. Some building owners, they just set their supply temperatures to whatever the design engineer has suggested, and they never follow up on them. So let's say they set them to 8 degrees, and regardless of what the actual cooling demand of the building turns out to be. So non-optimized building supply temperatures set points in many buildings. And that also then leads to the fact that the return temperatures could be anything between 9 up to 18. So there's many buildings that do not reach the 18 degrees. And some recommendations to avoid the low delta T is that it could be good to have flow restrictions on the primary side, and what you saw earlier, that not too much district cooling water should be allowed through the control valve based on what the maximum cooling power of the building is. And also that it's important to make sure that the building set points are 2 degrees higher than what the supply temperature of the district cooling water is. So if the district cooling side, let's say they can't keep the 6 degrees for a few hours, it might jump up to even 8 if they have troubles with production. Then the supply temperature has to follow on the building side. Otherwise, all the control valves will just open and let maximum flow through, and they're going to have even harder time to supply the cooling. And then also to summarize everything, all the learning experiences from Gothenburg, one main point is that if you have the ability to use absorption chillers based on waste heat or district heating water, then you want to make sure you have the highest possible delta T in the chiller generator, so you don't get problems with delta T on the district heating side too. It's enough with the cooling side. And also, if you can use free cooling in your district cooling system from the sea, from the river, then it's important to see what are the actual temperature requirements for the customers, and then try to maximize the usage of the free cooling based on what the customers actually need, because then you can have a much larger share of free cooling in your district cooling production. And on the customer side, it's advisable, or it's good if the district cooling provider actually owns the substation and all the control equipment of the district cooling customers, because it gives more control to see what actually happens. It's good if the temperatures, the building owners log their temperatures, but it's good if the district cooling provider also know what these temperatures are. So there's more of a data information communication between the two sides. And it could also be good to actually measure the flow depending on what that additional cost would be, of course, but to measure the flow in the building systems too, to be able to diagnose when something goes wrong. And then it's also important to provide incentives in terms of flow rate pricing and price models for the district cooling customers, for them to work with the temperatures and make sure they can become as high as possible for their buildings, and also to collaborate with them to find the best optimal solution for both district cooling provider and for the building owners. So with that, I want to say Aita. Thank you for listening.
Thank you very much, Jemima. Very interesting presentation. And actually, to summarize, I see that for Estonia, there are some possibilities to learn from your side. And the first one is the secondary system. So basically, similar to district heating, we have to take a look what happens in the customer side. So if in district heating we would like the customer to decrease the temperatures, then in the district cooling we would like the customer to increase the temperatures. So basically, what happens after the heat exchanger is extremely important.
Yeah.
The second thing is that, as you mentioned, you have experience of 25 years in Gothenburg, and now you have learned a lot. You made some mistakes.
Yeah.
Now you're changing something. So maybe for us, for Estonians, it's very good that if some regions we're starting to construct district cooling from scratch, so maybe we can actually make it in the correct way, as you advise.
Yeah.
So this is a good point of thinking.
Yeah.
And I very hope that today after lunch we're having the meeting in university, and we'll try to think out some good research and scientific projects, and we'll also learn from your side.
Yeah.
Thank you.
Great.
So actually we have some
questions
before the coffee break, so maybe someone would like to ask. I've seen that Margus from Forto was making such much pictures, so maybe it was interesting for you. So Margus, you are as one of the biggest experienced people in Estonia who you are managing district cooling in Tartu for so many years, and maybe you have some
comments.
So I used to ask from Maria during coffee break. Coffee break. Okay, it's personal.
Anyone else?
Okay. Maybe some other questions from Tirida's side. Oh, okay,
Yeah.
You use the water from the river. How do they green people react to that?
Actually, I don't think they know. That's
They will. They will.
Yeah, so there are environmental permits on how much water in terms of flow rate that can be used, but also how much the temperature is allowed to increase. So that could actually be an issue with the work that I'm doing if the temperature gets too high.
You are not go over that, I don't know, summer temperature is 60, 80. You are not go over this limit. How do you...
Yeah, well, right now the district cooling temperatures are so low, so they're not like much higher than the river temperature is. But that could be the issue in the winter. I don't know if that answers your questions.
So
to go over.
About the winter cooling, you are cooling in some business centers or something like conference rooms.
Yeah.
Or what for? Also.
Oh, yeah.
What for is using this cooling energy?
It's conference centers like this one in the winter, but also hospitals. They use a lot of cooling, and restaurants. But it's mainly comfort cooling, and some also data server where they have to cool the data equipment. Yeah. The cooling is quite low during the winter compared to what it is in the summer. Yeah.
What about technical conditions? If the customer asks for technical conditions for a district cooling company, let's say, why don't you rise the secondary temperatures for design already, so you can get better for district cooling system parameters, temperature parameters.
If the customer...
You don't give out 18.8, you give out 22.12, for example.
Yeah.
Why don't you do this?
Yeah, no, they... It's partly tied to the contracts that they promise the customers the 6 degrees, and they... but then, like we saw, they don't need it. Exactly. Yeah. Especially during spring. Yeah, exactly. No, that's what I think they should do, the district cooling provider. Especially during spring, when the river temperature is slowly increasing, but the cooling demands in the buildings are still low, and the outdoor temperature is still low, considerably low or fairly low, then they can, if they were to raise the supply temperatures in spring, they can use the free cooling for a longer period, so they can wait to turn on the chillers. But in the summer, the district cooling provider in Gothenburg, Göteborg Energy, they're not interested in raising the supply temperatures, actually rather the opposite, because so they can meet the maximum demand. But I think it's definitely interesting in the transition parts of the year, spring and fall. But it's a communication with the customer, and they haven't really had that sort of communication. They're like, okay, we're gonna give you 6 degrees all time of the year, and that's it. But they should start that. Yep.
Actually, if it's possible to add one comment to Julia's question, one remark. Actually, 1 year ago, we went to study the colleagues from Göteborg Energy with Vladislav to study district cooling from Göteborg. And to my mind,
okay.
you had such situation that, first of all, this question what you asked, that you had open system. So basically, you were taking like water from river and basically not to lose any degrees. So it run through the, there was no heat exchanger. So basically, this was the thing that we were doing. So you didn't want to lose any degrees because if you put some heat exchanger, so from the river you get 5 degrees, heat exchanger maybe you lose 1 degree, 1.5 or something like that. This was open system, and actually this water was actually damaging the devices. So this was a problem, and your colleague said that please don't make this like mistake in Estonia. Yes. So this was the first thing that you were doing, and now you put the heat exchanger there. And the second thing, actually, it's possible to calculate the environmental impact of this increasing water temperature. So it's quite easy to calculate. And Maria, you were mentioning that you have this river, but to my mind, this river basically is flowing to the sea. So the sea is actually nearby. So basically, you name it as a river, but basically it's a sea. So the situation in Gothenburg and Tallinn is quite similar. So basically, you're taking from river, but basically it's like a sea.
Yeah, it's the outlet to the sea.
It's nearby to the sea also.
Yeah, it's good that you clarified that. That's an important part, actually.